and these are the devices we are currently using. These are the number of devices which have been shown over here. Maybe we are using more than that, but this is one example. These are all coming under portable mobile devices. I hope my voice is audible to all of you. So as you are seeing that all these portable devices we are using right now, you know that they are mostly run by battery. Battery is the most important source of energy. So we should optimize in such a way that whatever the power consumption is happening, it should be minimal, and the battery should the timing will be more. So this is what I have shown you. This is nothing but the tear down part of Apple iPhone 14 Pro. You can see over here. So currently I am also having that phone. I am using that. So mostly this is the phone, and this, you probably know that wireless charging part is in the center. So you can see over here that part. This is the wireless charging part. And other than that, we are having different system on chip, we can say. This part, many are there. So I will be showing only one part of this as example, because they are all system on chip. System on chip means both hardware and software. We are having the interface and we are combinedly designing it. So there are multiple levels of consideration we may consider. So later on we will see what are the consideration we are taking or we are making. So this is one of the system on chip of that we can say iPhone 14 Pro Max. You see the number of modules which are there are many. So as I have told you that in the last diagram you can see, so we are having different SoC and different components. We have considered this part, and I am right now showing you different modules inside this particular SoC. We are having RF module, we are having antenna and everything in this part. So this is the tear down of, we can say, Apple iPhone 14 Pro. That not the whole part tear down, rather than one particular part we have considered for this example. So the point what I want to mention here is that we are having different modules here, and all the modules we are running together. So we require for the system, as a system designer point of view, I should design in such a way that the whole thing should consume less power. That is what the objective is. And this is one of the example we are showing the system architecture inside that Samsung mobile phone. You can see this is the SoC of Exynos 5, so which is based on CMOS 32 nanometer technology. So you probably knowing that different technological node we are having. So here it is 32 nanometer technology node, and this is what we are having multiple things inside that Samsung Exynos 5 SoC. So this is one of the examples. We are having everything there, from starting from that software part to that of hardware part. For everything we are including in this particular that is SoC, system on chip. Now if we see the embedded hardware design flow of any structure you can consider, whether it's portable mobile devices or any other gadgets, you will find that it will start with synthesizing with a Verilog SDL code or VHDL code. We can use VHDL or Verilog, that's up to you. And sometimes we are also using system Verilog. That depends upon you, us. For our requirement and what we want, we can use any other things. The complexity level may vary depending upon whether you are going for VHDL or Verilog or system Verilog. So then comes, we are having that technological independent optimization. Then we are having gate level optimization. So this particular part, this to this, they are coming under the front end part. or we are saying that front-end design. Mostly the people working in we can say Qualcomm, Intel, they work on back-end part, and sometimes they are working in the front-end part. So front-end part ends with netlist generation. Once the netlist has been created, like for example, we are designing a half adder. So we have created the netlist for the half adder. Then that netlist part concludes that front-end part. Then we will go for the back-end part, where we will start with the floor planning, routing and all. That's the most important part. There we can optimize everything. You see that optimization of power can be done at any level. Architecture level, system level, logic level, circuit level, even foundry level. Foundry level means silicon foundry we are talking about. The silicon level. We can optimize power in each and every level. So this part is related to the front-end part or front-end design, the first part. And the second part what we are having, this is related to the back-end part. So once the back-end part is over, once the layout is done, that GDS file we are sending it to that foundry, then they will take care of everything. So up to the GDS file, the back-end part comes to picture. Once the layout and the GDS file has been created, then we will send it to foundry, and rest of the things are considered by the foundry itself. We don't have to worry about that. Mostly in India, what we are having, the IC engineer, or we can say the core engineer, those who are working in Qualcomm, Intel, Texas Instrument, then comes your NXP. Mostly either they are working in this front-end part or this back-end part. And in India, the number of back-end engineers are more. If you consider Qualcomm or Intel, mostly they are working in 70% are working in back-end part, and rest 30% working in front-end part. And sometimes it also vary depending upon the company. Let's say for example, Synopsys is there. Synopsys is doing something different. They are helping Qualcomm and Intel in other way. So this back-end part, front-end part, the point what I want to mention is that this is one kind of embedded hardware design flow, where in each level we can optimize the power. In each level we can optimize the power. We are having different, this placement and routing, which is very critical in back-end design. If our placement is not correct, if our cell placement is not correct, if the routing is not correct, obviously more power will be consumed. That is what happens, and we have to optimize all these things. We have to place the cell, we have to route it. You know that even routing also very important part. If we are taking a longer wire, then obviously then power dissipation and everything will be more. So that's why we have to also optimize the route. Then as I have told that we are considering low power design. So first of all we have to understand what is the difference between power and energy. We can see over here, in this case the power is more. In this case you can say power or watt is somehow less. But you see the area under the curve, if you consider the energy, for both the case, whether this first case or the second case, area under the curve is almost same. See the area under the curve, see the area under the curve. As area under the curve is same, that indicates that the energy consumed by both the process are same. Whether we are having more power, if you think like that our mobile is running, suddenly we open up, let for example I am opening up my mobile phone, suddenly I am checking something, suddenly the power goes high at that instant. Then I am keeping in standby mode or switch off mode, depending upon that power consumption will be less. Let's for instance I am going for standby mode. Ultimately, although I am not consuming the power directly or at instant, but some power consumption is on. So for longer you will put standby mode also, then there are also energy dissipation. That is what if you keep even mobile phone 1-2 days without doing nothing in standby mode, the energy or the battery runs away. So that is what the concept is. Next, power consumption in IC, if you consider integrated circuit, we are dividing into three categories. One we are saying dynamic power, one we are saying static power, one we are saying short circuit power, which I have not mentioned. In the next slide we are having. So dynamic power, static power, and the short circuit power, they are three components, and they totally include that they totally adds up to give total power dissipation. So this is the formula for total power dissipation. This is the formula for our we can say that static power dissipation, where I leak stands for the leakage power and leakage current, and here this is the dynamic power, which is dependent upon the VDD and the capacitance and the clock frequency. All these three parameters are dependent for the dynamic power consumption. When the device is running, that means there must be some consumption and the power consumption will occur. So no doubt about it. Dynamic power consumption is okay. But again, we have to optimize in such a way that, say, by self-placing, routing, and each level, I can say, we will optimize in such a way that the dynamic power consumption will be less. Similarly, the static power consumption, even the dynamic power consumption can be controlled by the VDD. We can use less VDD. Let's, for example, we are using 5 volt VDD. The power consumption, if I use VDD as 0.8 volt, the power consumption will definitely reduce. So this is related to dynamic power consumption, which cannot be neglected. And static power dissipation comes to picture whenever we are going for short channel devices.